Welcome back to the Mechanics of Solids lecture series. In this series of videos, we're working examples using pressure vessels. In this example, a thin-walled cylinder with a radius r equals 100 millimeters and wall thickness t equals 8 millimeters is inflated to a pressure of 12 megapascals and also resists a compressive force F applied to the end caps. And here the illustration shows how the force F is applied. It's just an additional force in the axial direction. We're asked to find the longitudinal and hoop stress if F equals 0. Part B, the value of F so that the walls of the tank are in pure shear, and C, the ultimate shear stress if F is equal to 1500 kilonewtons. So let's just approach this problem one step at a time. The first part is fairly straightforward. We're asked to find the longitudinal and hoop stress, sigma longitudinal, which we know is PR over 2T, and sigma hoop, which we know is equal to PR over T. Let's substitute the known numbers. The pressure, 12 megapascals, times the radius, 100 millimeters, divided by 2 times the wall thickness, 8 millimeters, and that computes to 75 megapascals. Okay, the hoop stress, PR over T, perhaps we can recognize that it's just this value times 2, so 2 times 75 megapascals equals 150 megapascals, and that's the hoop stress. Okay? And we might hold on to those numbers as we need them in the remaining parts of the problem. Part B, find the value of F so that the walls of the tank are in pure shear. Okay, this is definitely a little bit more advanced, and we need to do a little processing to figure out what this means exactly. But first, let's find out how the applied force F affects the stress in the walls of the tank. And in order to do that, I should draw a free body diagram and go back to first principles, because this equation for sigma longitudinal is not going to apply exactly. So here's my free body diagram. Okay, sigma longitudinal, these are the stresses in the walls of the tank. I have the pressure acting on the walls of the tank, a P, which is going to act over the projected area, and then finally I'll add the end force. Summing forces in the longitudinal or x direction and setting them equal to 0. I have the longitudinal stress, which acts over an area equal to the circumference times the wall thickness, so 2 pi r times T, minus the pressure, which acts over projected area of pi r squared, and then plus the force equal to 0. Solving for sigma longitudinal, these two are going to switch signs. P pi r squared minus F divided by 2 pi RT. This simplifies to the PR over 2T that we had from before minus F over 2 pi RT. Okay, as I indicated, the second part of the problem is to figure out what do we mean by the walls of the tank are in pure shear. And it seems like that may not be possible, but based on a little stress block, the walls of the tank, pure shear means that there is a state for this, for the walls of these tanks where we can rotate and there will be only shear. There will be no normal stress. Okay, and it's obviously not the orientation I have shown, but if you remember, if we're pure normal stress and we rotate 45 degrees, we can get pure shear stress. So from a Mohr circle point of view, the conditions for pure shear stress mean that Mohr circle has to be centered over the origin so that you can rotate to a case where where there is only shear and no normal stress, okay? And that would be the pure shear stress. So if we draw a circle around that case, it means that 45 degrees from the pure shear, you have a pure normal stress, where the normal stresses are in each direction are equal and opposite. Okay, so the hoop stress, sigma hoop, would be the positive normal stress, and sigma longitudinal, since we have this force in here, could actually be negative. So what we want to say here is that pure shear will occur when sigma hoop, when sigma longitudinal is equal to the negative of sigma hoop. So that means my requirement is if sigma hoop equals PR over T, sigma longitudinal should equal a negative PR over T. And let me set that equal to PR over 2T minus F over 2 pi RT. Okay? Let's solve for F. I'm going to bring F over to this side. F over 2 pi RT is equal to, I'm going to bring this over to this side. I have PR over T plus PR over 2T. That's 3 PR over 2T. Okay, so F is equal to 3 PR over 2T times 2 pi RT. My 2's cancel, my T's cancel, and I'm left with 3P pi R squared. Okay, so let's solve for that. F equals 3 times 12 megapascals times pi times 100 millimeters squared. Okay? And if we crunch the numbers there, that should compute to 1,130,400. What are the units? Megapascals times millimeters squared would leave us with newtons. I'm going to convert it to kilonewtons. F equals 1130 kilonewtons. Okay? The last part of the problem is similar. It asks, what is the ultimate shear stress if F equals 1,500 kilonewtons? Okay, F equals 1,500 kilonewtons. What's going to happen here? F is greater than the force that was required for pure shear is actually going to make the longitudinal stress more negative. So we're going to have a situation something like this, where the ultimate shear, tau ultimate, is going to be, again, the radius of the circle, but appearing somewhere to the left of the origin. Okay, we can recall and use the equations that we found in part B. Sigma longitudinal equal to PR over 2T, and remember this was 75 megapascals, and sigma hoop equal to PR over T. This was 150 megapascals. Okay, so let's calculate, with the new given F, let's calculate this term right here. Sigma longitudinal equals 75 megapascals minus F, 1,500 kilonewtons. I'm going to convert it to newtons by multiplying by 1,000, divided by 2 pi. R is 100 millimeters, and T being 8 millimeters. And that computes to a negative 223.4 megapascals. Now we have our sigma hoop equals 150 megapascals. So this gives us, I'm going to draw this a little bit neater so you can understand. This gives us the principal stress in the positive direction of 150 megapascals, the principal stress in the negative direction of 223 megapascals, and then my Morse circle, I want this value, so I need to find, which is tau ultimate, I need to find the radius of the circle. Okay, so tau ultimate should be equal to sigma p1 minus sigma p2 divided by 2. That's the radius of the circle. 150 minus a negative 223 divided by 2. And that computes to computes to about 187 megapascals. That's our ultimate stress. Okay, that concludes this example.